Hey guys, Mr. B here. So this video is going to be the video lecture for the Chapter 9.2 notes. Again, this video is mainly so that if you just wanted to hear me talk about the information rather than just reading on your own, hopefully this will help you. Alright, so in this section we're going to be learning about naming and writing formulas for ionic compounds. This is a little bit of review. We did learn this in Chapter 7, but in this section in particular we're going to be learning how we use transition metals as well as how we use polyatomic ions. Okay, so when we get to those parts I'll probably slow down a bit more because the beginning stuff is sort of stuff we've already done. So first we'll be learning about naming binary ionic compounds. Binary means that you have a compound made out of two different elements. Okay, so examples of binary compounds would be like Na2O. Okay, so it'd be sodium oxide. This has two elements, sodium, oxygen. Another example of a binary compound would be like Ca3N2. So this would be calcium nitride. Again, you have two elements there, so binary, right? Bi means two. An example of one that is not binary would be like Al2SO4 This would be aluminum sulfate. This is not binary because we have three elements, aluminum, sulfur, and oxygen. Okay, so at first we're just going to be talking about binary compounds. Primarily this means we're dealing with the metals and the nonmetals on the periodic table, right? So this is metal, nonmetal. We're just looking at regular elements on the periodic table. We're not looking at polyatomic ions at all. Okay, that's what this means. So not this one. How do we scratch that out? Apparently I can't. Okay. Maybe I can. Nope, I can't. All right. Anyway, whatever. Not that one. Okay. Disregard that one. So, there's a lot of names in chemistry when it comes to chemical compounds, and a lot of the names are common names. So gypsum, for example, is a common name. That is, I think, calcium carbonate, which, when you hear common names, they don't really tell you anything about the chemical composition. Another example of a common name that you probably have never thought about is water, right? If you hear the word water, obviously a lot of you know that that's H2O, but if, let's say, for example, you were from another planet where water didn't exist, and you came to this planet and someone was like, hey, would you like a glass of water? You'd be like, what is this water you speak of? What is it made out of? I don't know. Whereas if I said, oh, would you like a glass of, dihydrogen monoxide? Now, we haven't talked about molecular names yet. That's Chapter 9.3. But dihydrogen, hydrogen, monoxide, oxygen. So hydrogen, oxygen. Just by hearing that name, you can probably pick out some of the elements in it. Oh, dihydrogen monoxide. So there's probably hydrogen and oxygen in this compound. That's like the formal name for water, or at least one of them. Okay, so there's a lot of common names we use in chemistry. We're going to try to stay away from those because we want to understand formal names, because formal names give us a better idea of the composition of the compounds. We can write a chemical formula for it. Okay, so again, a binary compound is composed of two elements, can be either ionic or molecular. We're only going to be dealing with ionic compounds in this section. Chapter 9.3 will cover molecular ones. Okay, to name binary compounds, you place the cation name first, so that's the positive thing first, anion thing second. Okay, so positive thing first, negative thing second. Example of this again, and I gave two already, but I'll give you even some more. So examples of this would be like Al2S3. So aluminum, which is the cation, that's the positive one. Sulfide, that's the anion, that's the negative one. Okay, positive thing first, negative thing second. One more example, we can do like K3P. So this would be potassium phosphide. Potassium, positive thing first. Phosphide, which is phosphorus, but remember that anions end in "ide." That's the negative thing, goes second. Okay, that's it. When it comes to naming, we'll take a look at how we write the formulas here in a second. But name the metal first, anion thing second, has to end in "ide." Okay, or at least for these ones they do, because we're not dealing with polyatomic ions. So here's an example: tin 2 fluoride. Now this tin 2 Tin, remember, is a transition metal, so it has more than one charge. So it needs a Roman numeral. The Roman numeral here is indicating that the charge on the tin is +2. Okay, and we can see here that we have Sn, which is tin, F for fluorine, which we call fluoride. So tin 2 fluoride is how we would name it. Again, we're naming positive thing first, negative thing second. Here would be an example of tin 4 sulfide. Again, as to how do we know it's tin 4, we'll take a look at that later on. And I have a video of me going over the questions in this section where I really outline how you determine the charge on the transition metal. But for right now, I'm not going to go into that. I'll go into it probably in a little bit later. Okay, so we have tin, so tin 4, and then S for sulfide. So again, we're naming positive thing first, negative thing second. Okay, one more. So hematite, this is a common name. Hematite is what we call iron ore. Obviously, the name hematite doesn't really tell you anything about what's inside of it. Now, some of you might know what hematite is. Maybe you have some hematite. You're a rock person. But it doesn't tell you that it's made out of iron or oxygen or iron 3 oxide. Okay, iron 3 oxide, however, that gives you much more information. We have iron 3, so we have iron, and then oxide, which is oxygen. So this gives us more information about what it's actually made out of, whereas hematite doesn't really do that. Okay, again, I have videos on the practice problems, or a video on that, so you can go watch that if you want to know how we answer these questions. All right, as for writing formulas for binary ionic compounds, we're going to write the symbol of the cation first, then the symbol for the anion second, and then we need to balance the charges, and we're going to write little numbers down below. We call these subscripts, that indicate how many of each element we have in the compound. Okay, so here's an example for you. Let's say that we wanted to write the formula for lithium phosphide. Okay, lithium phosphide. So we're going to write the symbol of the cation first. So lithium symbol is Li, and it makes a charge of +1 because it's in column 1 on the periodic table. Phosphide is phosphorus, so that symbol is P, and it makes a charge of 3- because it's in column 5. Okay, and all of those make a -3 charge because they need to gain 3 electrons. So from here, we need to then balance the charges. If we look at this, we have a +1 and a -3. In order for this compound to form, we need to have the same total positive and same total negative. We have +1, -3. We have more negative than we do positive. So in order for us to make this compound work, we're going to need to have more positive lithiums to balance out the 1 negative phosphorus. So if we had 3 lithiums, that would make a total of +3 to balance out the -3 from the phosphide. So our chemical formula is going to be Li, and then we're going to put a little 3 down below to indicate we have 3 lithiums. Again, we have 3 of them because together they are +3. And then we have 1 single phosphorus because it has a charge of -3. So the 3 lithiums make +3. The 1 phosphorus is -3. Those are balanced out. So our chemical formula would look like this. And the subscript is this little 3. Okay, that's a subscript. That indicates how many. Now you'll notice that on the P, I don't have any number. The number would technically be a 1, but in chemistry, we don't write 1s just because it looks kind of weird and it's like the grammar, okay? So you don't need to write a 1. If you write a 1 just because like it makes you feel better, I'm not going to count it as wrong, but I can tell you right now it's grammatically incorrect. So if there's no number there, then it's just a 1. The 1 is assumed, okay? All right, so let's take a look at some examples here. We're going to delete this picture so that we can actually write here. Let's insert a text box so we can do so. All right, so it says, write the formula for these binary ionic compounds. So for letter A, nope, we don't want this italicized. For letter A, copper 2 sulfide. All right, so copper 2. So copper has a symbol of Cu. And if it's 2, that means that it is 2+, okay? It's a transition metal. It makes more than 1 charge. That's why there's a Roman numeral. Whereas sulfide is sulfur. That has a symbol of S. And it makes a charge of 2- because it's in column 6, okay? And every element in column 6 gains 2 electrons to get to 8. So they all make a charge of -2. Now, in order for this to work, we need to make sure the charge is balanced. Now, luckily for us, we have positive 2 and negative 2. Those are already balanced. So we only need 1 copper and 1 sulfur to pair with each other because their charges happen to already be balanced. So our chemical formula is going to be 1 copper and 1 sulfur, and that's it. Okay, just CuS. We don't need to write the 1s because the 1s are implied. And that's it. Okay. For letter B, we have potassium nitride. So potassium is K. It makes a charge of positive 1. It's in column 1 on the periodic table. Potassium does not have a Roman numeral because it is not a transition metal. It's not in the middle of the periodic table. It doesn't make more than 1 charge. It only makes a charge of positive 1. Nitride is nitrogen. That is a symbol of N. It's in column 5, which means it needs to gain 3 electrons to get up to 8. So it will make a charge of negative 3 as an ion. Okay, so if we look at this, we see that we definitely have more negative than we do positive, right? We have negative 3, positive 1. We need to balance this out. So we're going to need to have more potassiums to balance out with the nitrogen. We're going to need to have a total of 3 potassiums to give us a positive 3 to balance out the 1 nitrogen, which is negative 3. Okay, so our chemical formula is going to be K3 and then 1 single N. So just K3N. Okay, that's our chemical formula. Now, one real quick trick, by the way, if you didn't realize this already, is if you don't want to think about like, well, how many of this do I need to balance with how many of this? You can do what I call the Wonder Woman, which is you take the 2 charges and you bring them down like an X, right? And I call it the Wonder Woman because if you ever watched Wonder Woman, she would block bullets with her bracers and she would do this. So she'd make like this little X. So you take the charges of each ion and you drop them down and you switch them. Okay, and then you get rid of the plus and the negative. So, and then you have to you have to simplify the numbers at the end. So like, for example, this was K with a +1 and N with a 3. The 3 goes down onto the K, as we see here in the formula, and the 1 from the K goes down onto the N, which we don't write it, but we see it there. Okay, on this one, this 2 from the copper would go down on the sulfur, and this 2 from the sulfur would go down on the copper. And then the last thing you have to do is you have to simplify or reduce the numbers if you can. So in the first one, since it was 2 and 2, you could put 2 and 2 down here, but then since they're both 2s, you can divide a 2 from both and they'd simplify down to 1, which is why in the chemical formula there's no numbers. Okay, so that's what I like to call the Wonder Woman or the cross and drop method. It's just a really fast way to do it, so you don't have to think about like, well, how many of these and these do I need? But anyway, okay, so again, there's some practice problems. I have a video of me going over them, so I'm going to skip past them for right now and keep on talking about the information. As for writing formulas for compounds containing polyatomic ions, we're basically going to do the exact same thing. The only difference is that when we write the formula with the polyatomic ion, we have to have parentheses around the polyatomic ion to kind of show it. Okay, so it kind of it's like in its own little bubble. So we're still going to write the cation first, the polyatomic ion second. We still have to balance charges. So here's an example for you. Let's say we wanted to write the chemical formula for beryllium carbonate. Okay, actually let's do a different one. Let's go beryllium nitrate. All right, so beryllium makes a charge. So first, beryllium symbol is Be, and it makes a charge of 2+ because it is in the second column on the periodic table. Nitrate is a polyatomic ion. We know that because it ends in 8, and all well, not all, but most polyatomic ions end in 8 or ite. If it was nitride, that would be regular nitrogen. But nitrate should be a red flag that this is a polyatomic ion. You can find it on the back of your sheet. Nitrate has a chemical formula of NO3 and a charge of -1. Okay, so when we put these two together, we notice that nitrate has a charge of -1. Beryllium is +2. So we have more positive than we do negative. We need more nitrates to balance out the beryllium. Or if we do the cross and drop or the Wonder Woman method, we can take the 2 from the beryllium, drop it down onto the nitrate, take the 1 from the nitrate, drop it down onto the beryllium. So we write a formula. We have Be with a 1 on it, which we don't need to write, and then NO3 with a 2. And to show this, we're going to put NO3 in parentheses, and the 2 is going to go outside the parentheses. Now, the reason why we do this is if we don't do that, and we go NO2, right? We go like, oh, well, let's just put the 2 right there, right? Like we just put the 2 down onto the nitrate. Well, if you do this, this now isn't nitrate anymore, right? This is NO2. That's nitrite. That's a whole different compound. If you change that 3 to a 2, you've completely changed the compound into something different. And we can't do that, okay? So this has to be a 3. And if we don't put the 2 outside parentheses, so if we don't do it like this, instead we go, well, what if we just put the 2 like that, right? Let's just put NO3 then with the 2 on it. Well, that looks like NO32. There definitely is not 32 oxygens here, so we don't want to do that either, okay, because that's confusing. So we have to put the 2 outside the parentheses like that, and we do it as a small 2. We don't want to do it as a big 2 like that. That looks kind of weird. As well as later on, we're going to learn about big numbers that get put in formulas like this, and those are reserved for something completely different, okay? So we need to have a small 2 like that. But either way, this indicates that we have 1 beryllium with a charge of +2 and 2 nitrates. Okay, these are like groups of things. There's 2 of them. Each one is -1, so that gives us -2 total with a +2. That balances out. Okay, so here's another example. We have calcium nitrate, so Ca with a 2+, nitrate NO3 -1. It's basically like the example we just did, but instead of beryllium, we have calcium. Either way, though, it shows that we need 2 nitrate ions, each with a charge of -1 to balance out the +2 charge from the 1 calcium. So the 2 nitrates will give us a total of -2, and the 1 calcium has a charge of +2. That would balance out. In our formula, we'd show that we have 2 nitrates here outside parentheses and the 1 calcium. And of course, the 1 isn't written because it's implied. Okay, so calcium carbonate is a compound of the polyatomic ion. It's found in pearls and their shells of oysters. Lead 2 sulfate is a compound for automobile batteries. I'm going to write these out here real quick too. So calcium carbonate, calcium would be Ca with a charge of 2+. Carbonate is a polyatomic ion with a charge, a formula of CO3 2-. So if we were to write this out as a formula, calcium is +2, carbonate is -2. Those would balance, so we'd need just 1 of each. And so we would get CaCO3. 1 calcium, 1 carbonate would balance out. There's our formula. Okay. Lead 2 sulfate. Lead 2 would be Pb. Oops, sorry, do this in red. So Pb, 2+. And then sulfate is a polyatomic ion. It has a chemical formula of SO4 and a charge of 2-. So in this case, again, we have +2, -2. Those would balance out in a 1-to-1 ratio. So we just need 1 of each. So 1 lead and 1 sulfate. Now you'll notice that I don't write this sulfate in parentheses when there's only 1 of them. You only have to write it in parentheses when there's more than 1, and you have to put a number outside. If there's only 1 of them, you can just write it as SO4. You don't need to have parentheses around it. So, okay, here's some more examples here. So again, let's insert a text box. We can do some typing. So magnesium, so it says, what are the formulas for these? So we have magnesium hydroxide, potassium sulfate. So magnesium hydroxide, magnesium is Mg. It makes a charge of 2+. It is in the second column on the periodic table. Hydroxide is a polyatomic ion. It has a formula of OH and has a charge of -1. So we can see that we have +2, -1. Those are not balanced. We're going to need to have 2 hydroxides to balance out the 1 magnesium. So we have Mg, and then we're going to put parentheses around the OH, and a 2 goes outside to indicate we have 2 of them. Again, if we do something that looks like this, now it looks like it's OH2, which is a whole different formula than just OH, because OH has 1 oxygen, 1 hydrogen. OH2 has 1 oxygen and 2 hydrogens. That's not the same thing anymore, okay? We can't do that. So we have to put the 2 outside parentheses like this, okay? That's the main thing to remember. For B, we have potassium sulfate. Potassium is K and makes a charge of +1. It's in column 1 on the periodic table. Sulfate is a polyatomic ion. It's on the back of your periodic table, and it makes a charge of -2. Again, if we look at this, we have +1, -2. Those are not balanced. We're going to need to have 2 potassiums to balance out the 1 sulfate. So we have +2, -2. So we're going to have K, and we're going to have 2 of them to get +2, and then 1 sulfate to balance that out. So K2SO4. Okay. Again, we can also do the Wonder Woman. So we can take the 2 from the sulfate, drop it down onto the potassium so it's there in the formula, and then take the 1 from the potassium, drop it down here on the sulfate, which we don't need to write it, so that's how we just have SO4. Okay? All right. Lastly here, naming compounds of polyatomic ions, basically just like naming any other compound. You state the cation first, the anion second. In this case, the anion is going to be a polyatomic ion, most likely, because most of them are negative. The cation could be a polyatomic ion, though, because there is one polyatomic ion that is positive. That's ammonium. So, but you're still naming cation first, anion second, just like you did in the other ones, okay? So, one example here, or I'll give you 2 examples. So, one we could have would be like, MgNO, let's go, MgNO3, 2. Okay, so to name this, we would name Mg, which is magnesium, and then we would name NO3, which is nitrate. Okay, so this would be called magnesium nitrate. We could do, so here's another one. We could do NH4, C2H3O2. Now this one looks really crazy. You might go, what the heck is this? This is just 2 polyatomic ions put together. NH4, this is 1 polyatomic ion. That's ammonium. You can find it on the back of your periodic table. It's a positive one. Okay, it's a positive polyatomic ion. And C2H3O2 looks really crazy. That's just another polyatomic ion. It's called acetate. It's found on the back of your periodic table. Okay, and you can put 2 polyatomic ions together, +1, -1, stick them together, just like you'd stick together any other, ionic compound with a positive ion and a negative ion. In this case, just happens to be 2 polyatomic ions. Okay, one more example here. Let's do kind of a hard one. Let's do TiO2. Okay, so TiO2. So to name this one, we name the cation first, which Ti is titanium. Then the anion second. And actually, you know what? This is not a polyatomic ion, so we're going to change this. Let's go TiCO3. And we're going to have a 2 outside the parentheses. So there you go, like that. All right, so Ti is titanium. CO3 is carbonate, polyatomic ion. Now, titanium is a transition metal. So even though titanium carbonate sounds pretty good, we do need a Roman numeral for the titanium. Now, this is where it gets tricky because we have to figure out the charge of the titanium. We don't know what it is, but basically we can think of it like this, okay? So we have a titanium ion, which has a charge of question mark, right? Because we don't know the charge. It's positive something. And then we have carbonate, which we do know the charge on carbonate, and it's 2-, because that's the charge that carbonate always makes. And we have 2 carbonates, okay? We have 2 of them. So we don't just have 1 CO3 2-, we have 2 CO3 2-, right? We have 2 of them. So we have 2 carbonates. Together, they make a charge of -4, right? Because each one is -2. That's -4 total. And we have 1 titanium, and that titanium has to balance out these carbonates. And if these total are -4, then the titanium has to be +4. Okay? That's how we can determine what the Roman numeral is for the titanium. So this titanium would be titanium 4 carbonate. And again, we find that by looking at what the titanium is bonded to. We know the charge on carbonate. We have 2 of them. So this is a total of -4, which means the titanium has to be +4 to balance it out. That's how we can find the Roman numeral, okay? This is probably the most difficult thing that students struggle with, is finding the Roman numeral or the charge on transition metals. So I would definitely look at doing some practice on this, and there are some practice problems in the notes here where I go over that, so you might want to watch that. Okay, the last slide here just shows one more example of a polyatomic ion, or a compound with a polyatomic ion, sodium hypochlorite. That is bleach. Okay, bleach is a common name. Obviously, if you hear the word bleach, that doesn't really tell you what's in it, but sodium hypochlorite is the formal name for bleach. It's a sodium ion bonded to a hypochlorite polyatomic ion. Okay, so sodium has a charge of +1. Hypochlorite has a charge of -1, so they would balance each other out in a 1-to-1 ratio. So you need 1 sodium, 1 hypochlorite. You put them together, you get NaClO. Okay. All right. Anyway, that is the end of the notes here. There are some practice problems, and again, I have a video of me going over those. So if you want more practice with that and you need more understanding, go watch those for sure, and hopefully that will help you. All right. If you have any other questions, as always, you can email me, ask me. I'm more than happy to help. And I will see you in Chapter 9.